My name is Ryan Campos, and this is my video project. Alrighty, so my project question was, how does the mass of an object rolling off an inclined plane affect the kinetic energy it has once it is off the plane? In order to solve this question, I made a list of the variables that would be included in my project. So for the independent variable, or the thing that's going to be changing in my project, is the masses of the objects. And for my project, I chose balls for the objects. So I'm going to basically be having different masses of balls that I'm going to be rolling down an inclined plane in order to find kinetic energy. And therefore, dependent variable would be kinetic energy, but really it's velocity in this case, because that's what I need to calculate the kinetic energy. And to do this, I'm just going to have to time how long it takes for the ball to roll 1 meter at the bottom of the plane, and just do 1 meter divided by how many ever seconds it took, and I'll be able to find velocity and then plug it in the equation for kinetic energy and find kinetic energy. And so for the control variables of my project, it would include angle of incline, spot of incline where object is placed, size of object, and shape of object. So these are all things that I'm going to keep the same. And doing this, I'm just going to use a tape measure to keep everything constant. In order to calculate the independent variable of the masses, or which is the masses, I'll be using an electric scale, as you can see on the screen. And I'll just put the ball on top and just write down how much it weighs, translate into kilograms, and yeah. To calculate the dependent variable in my project, which is velocity, I'm going to be using a timer on my phone and a tape measure, as you can see on the thing. And I'm going to start the timer at the beginning of the tape measure and then stop it once it reaches the 1 meter mark, which I looked up and it's approximately 39 point something inches, which I have marked for the tape measure. So to make sure the control variable stayed constant, I made sure to use balls that were similar size and same shape. As you can see on screen, they're similar size and the same shape. And these were some of the balls that I used for my trials. They all weigh different. As you can see, they're different materials. I also marked where on the slope I would drop each ball, just so that data would be constant as well. Here's a quick overview of what my project looked like. So I had the tape measure right there. Here's my slope. I held it up with a cinder block that I had. And yeah, that's basically it. This is my first trial of my lightest ball, as you can see. And this is my final trial of the heaviest ball. And I have a timer in my left hand right there. Yep. So I sort of already said how my thing's going to work, but the trials might have been too fast to tell what was happening. So I have my slope here, just a piece of wood to hold it up. So it is a slope. I got a cinder block right here. And right here, I had something to hold the ball up. And I had it right here, and then I just let go and let the ball roll on its own. And I have this tape measure right here at 1 meter. So with my phone timer in one hand, and the thing that held the ball up right here on my left hand, I would let go. I would wait until it got just before it crossed right here. I would start the timer, let it roll, and then stop it as soon as it passed the 1 meter mark. And then I got like a little skateboard to stop it, so I'd have to go right after it. Here's just me including a video of me weighing the masses of some of the balls that I used. And so this electric scale measured in grams, so all I had to do was just convert that into kilograms for my data. This is my data for my project. So right here, I got the mass of each ball. We had to do 7 data points, so I have some masses. And right here's the average time to roll 1 meter. And so I rolled each ball 3 times and just calculated the average just so I get less error on it. And right here, it all travels 1 meter. And then here's my dependent variable of the velocity of the ball, which I use to calculate the kinetic energy. And then the mass of the balls are the independent variables. And so to calculate kinetic energy, I basically used the velocity in this equation, plugged it in. Here's an example for the first ball, calculating its kinetic energy in joules right here. And then one pattern I saw was that for whenever the mass of the ball increased, the kinetic energy of each of the balls also increased. This is my data graphed on a piece of graph paper. The title of the graph is Effect of Mass on Kinetic Energy. And on the y-axis, I have kinetic energy in joules. And then on the x-axis, I have massive balls in kilograms. And I got it situated right here. Each square is going up by 0.01 kilograms. And then each square on the y-axis going up 0.05 kinetic energy in joules. And so I got my graph right here. And basically, looking at it, I drew a best fit line. The relationship my data has is as mass of the balls increase, the kinetic energy in joules also increases. And it looks to be exponential, like slowly starting up here and then exponentially getting bigger. And this would make it a direct relationship, direct and proportional relationship. As the mass of the balls get bigger, so does the kinetic energy in joules. Error could have happened in my project. I wouldn't be surprised. And it would probably be right here in the average time to roll a meter because of human error and my ability to start and stop the timer when the ball first crosses the tape measure and then finishes crossing it. This could affect the velocity of the ball and my calculations overall and affect the values on my graph. But with that being said, I'm still confident in the relationship that my data shows, but just not to the extent of the exact numbers. Right here is my error analysis and my error percentage and combination percentage. So I got the percent error for distance and the percent error for time, and it combined. And it's around the 20s up towards the almost going to the 30s. So I'm not too confident about it. And for the kinetic energy, here's some max and minimum values according to the percent errors. And then I put that on my graph on the range that it could have been based on the errors. Right here. My errors were human errors, so there wasn't too much I could have done to lower it. But one thing is recording the trials with slow motion on my phone and putting in frame where the ball first crosses the mark of the tape measure and where it crosses the 1 meter mark. And doing this, I could look back at an exact, more precise time that it crossed the 1 meter mark instead of just freehanding it with my eyes and finger. I use the error analysis guide on Google Classroom to calculate my error percentages and with that my calculator. And that's it for my project. Hope you enjoyed.